Hello, my name's Ian, and today I'm building a digital frequency generator. Compare that to the last project, which was an analog frequency generator, a rather disappointing analog frequency generator. Nope, this one's digital. That means there's going to be some coding as well as building a bit of hardware. And talking of hardware, let's look at some of it. So here we have it all. Going to be coding an Arduino Nano. This is the digital frequency generator. This is an AD9833 module. This particular module from DollaTek has an onboard amplifier and a digital potentiometer to control that. We'll be controlling all of this through the SPI bus from the Arduino. Controlling it will be with a rotary encoder, and this is a nice rotary encoder. It's a breadboard friendly module. Easy to wire up, easy to control. It's got a push button as well as obviously the turn motion, so it clicks as well. Displaying everything will be on a 4x20 LCD module, this module here. This module is the big brother of the more regular and standard and seen everywhere 16x2 LCD module. We'll be connecting to this via the I2C bus. Now that's thanks to a little module which will be on the back. This is a little module that takes a blizzard of wires that the LCD modules usually need and converts it to 4 wires, 2 of them for the I2C and then obviously ground and power. Connecting all of this together will be onto a breadboard. I'll be using some of these to go to the off-board modules and building the wiring with these little jumpers. I've got a wee kit of those already pre-cut. Let's have a look at what I will actually be attempting to build with you. There you see it. We've got the breadboard. This is a Fritzing schematic. Actually, Fritzing's very good for drawing breadboard schematics, and it's showing all the wiring that's going to be. This is the AD9833 module. This is my rotary controller, obviously the Nano, and there's my LCD, and there isn't a lot of wiring going on. So whenever I've done this wiring and a little bit of soldering, I will be right back. See you soon. Okay, I've done some soldering on the AD9833 module. I've also done some wiring on the breadboard. Let's take a look. Here you can see the module. I've got the frequency output pins on the top of it and the Arduino control pins on the bottom. It's not in flight at the moment, but what is in flight is the rotary encoder and the LCD module. You'll see it's wired up just for those at the moment. One wiring error from the previous drawing that you may have seen. I2C bus uses pins A4 and 5, not 3 and 4. Anyway, that's corrected in the drawing and also correct on this board. Now, these two modules are in flight. Let's look at some code. Only the encoder's in flight and only the LCD's in flight, so we've only included those libraries. Those libraries come with extensive examples, so take a look at them. I've used them to construct the rest of this code and we'll run through it. We'll skim it. So I have a lot of defines. I've defined all the pins, whether I'm using them or not. You'll see some will be in use later on for the SPI bus, etc. And some are in use now for the I2C. What you'll also see is I have to create encoder button objects and an LCD object. These are then used later on to update and read these modules. I've got a few global variables. These variables are global simply because the encoder is the one that changes most of them. It's interrupt driven, and global variables are easier to update via interrupts. Into the setup, we sort out the serial port, we do a wee bit of printing on it, and then this is the important bit for the encoder. We have to set up a few handlers for running in the background, interrupt driven. We've got one for clicks, that's single and multi clicks. We've got one for a long press, that's when you hold the button down and hold it for a while. You'll see that in a moment. And then we've got a handler for the encoder itself when you turn the knob clockwise or anti-clockwise. The encoders are quite clever. They know what way it's being turned, so it allows you to increment and decrement. In my case, it'll be the frequency or the gain. Then we set up the LCD, initialize it, turn on the backlight. We'll see that in a moment. In the loop, not a lot happening here. It's all interrupt driven really, and we'll see the interrupts, the interrupt handlers down below. But if they do change anything, they set a flag, and then if that flag is set, we update the LCD with some new information, and we send same sort of information out to the serial port. This is from the straight out of the rotary encoder example. You run that every loop. So I did. This is the first handler now. We've got this is the click, so this is click or multi-click. I'm only worrying about if it's a single click or not a single click. If it's a single click and you're in frequency mode, we'll see how to change the mode later on. But if you're in frequency mode, a single click changes the step. The frequency in this generator in this code is going to go between 0 and a megahertz, and updating the frequency 1 hertz at a time gets pretty sad pretty quick. So I can step, single clicking, I can step through frequency steps, basically frequency deltas, so I can add 1, 10, 1,000, 10,000 or 100,000. You'll see that in action. If we're not in frequency mode, the clicks alter the gain. I've got 3 steps for the gain: 0, midway, and 255, and they're just quick ways to get to the top, middle, and bottom of the gain range. It's only an 8-bit number, and that does it. You can still alter it with the rotary encoder, turning the knob. You can alter it up and down, but this is just a quick way to get through the range. If it's not a single click, it's what we call a multi-click, and we change the wave type. The module, the frequency generator module, actually supports sine, square, and triangle waves, but I'm only interested in sine and square. So basically, if I double click, it will toggle me between a sine and a square. As simple as that. And then of course the handlers change something, so it sets this flag to be true, so that the loop spots it and prints out the updates. This is the long press event. All it does is toggle the frequency mode. What that means is if I long press it, it'll toggle it between the rotary encoder changing the gain or the frequency, and that's just a toggle. You'll see on the screen I move a little arrow as well to show which one is in force at the moment. And then we have the encoder event itself. This is when you're turning the knob, and what it does is if you're in frequency mode, it adjusts the frequency. If you're in gain mode, it adjusts the gain. Simple as. And of course, both of those, it was changing something, so it set that flag. Now, I have downloaded this code to my Nano already, so we'll flip back to the hardware and have a look at it in action. So if I plug in the power for the LCD and then reset my Nano, and I apologize, but it's hard to read the LCD screen. It's just the camera and the LCD, it just does not work. I've played with the contrast to no avail. But what you can see hopefully is it's got a wave type of square. It's got a frequency currently of 1,000 hertz, and there's a step of 10 and a gain of 128. And as I turn the knob, you can see the frequency changing. If I double click it, you can see that it's changed the wave type. If I double click it again, it's now back to a square. If I long press it, that little arrow moves, and now I can change the gain. If I click, I can jump the gain through those different low, medium and high. If I long press it again, we're back to the frequency. And if I single click it, I can step up through the steps of the frequency, and you can see it's up quite large now, so I can change it quite quickly. And there we go. That's the code, the hardware so far. What I'm going to come back with next is the frequency generator, and we'll see some of its output on the oscilloscope. Until then, I'll be back in a bit. Okay, I'm back. The AD9833 is connected to the Arduino. Let's take a look. Here we have it. Wires going in, wires coming out. The wires going in are from the SPI bus of the Arduino, and also some select lines. There's two select lines because there's two modules on this that are controllable. One is the frequency generator itself, and the other one is a digital potentiometer. So the AD9833 is just the frequency generator. The digital potentiometer is an MCP41010. Output, we've got before the amp and after the amp. Let's have a look at the fritzing drawing to remind ourselves of how this is all connected together. It's wired up exactly as per this drawing now. So we've got the module for the LCD, we've got the module for the frequency generator with its before and after. We've got the KY040 module, which is the rotary encoder. We've got our friend the Arduino Nano, and we've got these wires that leave the board to go to that module, these wires that leave the board to go to the LCD. The KY is on the breadboard. Now, I've done the code as well, so let's have a look at the code. All I've added is the AD9833 and the MCP41010. Goodness me. So again, we're using libraries because the hard work's been done. We're standing on the shoulders of more giants, so I'm including those libraries. I then have to instantiate a couple of new objects. One for the frequency generator, one for the digital potentiometer. I then have to initialize both of them. So this is initializing the frequency generator, and this is initializing the potentiometer. The rest of it's pretty much the same, except I'm picking up a few functions that will give me the wave. Instead of me relying on my variable, I've set the module will tell me what it's set to. Okay, I think actually that's just a variable that's maintained in the library. There isn't any reading back from this module because only the transmit line of the SPI bus is connected. The receive isn't actually connected at all, so there's nothing coming back from the module. It's a fire and forget, I would presume. Everything else in the code is the same. You'll notice that there is a little bit of commented out code. It is possible to program the MCP41010 directly on the SPI bus, and that's what these sorts of things do. And there's a function here that it can call. I'm using a library, but it's not too difficult to do on your own without the library, but I'm using libraries for everything else, so I thought I'd use it for this one as well. And it's not a difficult library anyway, keeps everything consistent too. Now let's have a look at what we're getting on the oscilloscope. So this is the important one. So at the minute we've got nothing, and that's because I haven't connected anything up to these wires. So let me get a couple of probes. I've got two probes, blue probe, and the blue line on the screen will be for the output from the thing before the amplifier. So let's connect up the blue probe, and there we go. So we are getting a square wave. You may not be able to read the screen, the LCD screen that is. Frequency of kilohertz is programmed. It's mid gain 128, and it's a square wave. And we can see that on channel 1 we do indeed have a 1 kilohertz frequency, and it's a square wave. It's actually not a bad looking square wave, 4.5 volts peak to peak, and that's just the raw output. And the duty cycle is pretty much on the money, 50-50. Now let's connect up the other probe, and this is the amplified output. And if I just connect that up, there we have it. Oh, and what do you know, we've got another square wave. Excellent. It's a little bit bigger. No, it's exactly the same size actually. It's 128 gain. Let's see if we can change the gain and see what that looks like. So I long pressed to change the gain. Actually, you know what? For a square wave, that gain doesn't seem to have a lot of. Yep. You either have gain. Yeah, we've got gain. It looks like the gain on the square wave is topping out at about 42. About 42. And it's not bad. Not bad at all. Let's try a sine wave. So to get to a sine wave, we double click. And there we go. If we change the volts per division, I'm triggering on the blue one, so I have to change the volts per division to get in my trigger. There we go. 500 millivolts per division is triggered. Let's try the gain on that. So I'll use my step gain, which is clicking I'm on gain mode because that's where the arrow is. And if I go to, it's 42, I'll go to 128, there we go. Go to 255. If I start winding her down, yeah, I can see that falling. Excellent. Super stuff. Midway. Perfect. I'm really pleased with this actually. That's a nice sine wave. Now, we haven't played with any frequency yet, so let's start turning the frequency up. So I start increasing the frequency. Yes, that's increasing. Okay, let's increase it a bit faster. It's only on a step of 10 at the minute. Let's make it a step of 100. And oh yes, look at that. Let's make it a step of 1,000. Oh yeah, and a step of 10,000. Oh, I'll better wind this time base out a wee bit. There we go. And if I make it another 10,000, oh yeah, and let's try a step of 100,000. So the moment if I wind that out a bit more, now it's given me a frequency on this scope of about 124, and that's actually pretty much bang on the money. 123.7 it says there, and at 123.7 there. Oh, that's really good actually. Let's try see what the square wave looks like. So we'll double click for that. Now the square wave is a lot bigger, so we'll turn down the volts per division there. And where we have a square wave, let's same frequency. Let's turn that frequency up, see how high we can go. Actually, on the frequency, the software is set for 0 to a megahertz. And that's because, according to the data sheet, that's what the square wave can do. Apparently, the sine wave can go higher, but I've just coded it the same maximum. So if I change that time base When we start seeing the square waves rounding off a little bit on the red one, which is the after the amplifier. Let's see what it, look, we go into that. Wow. So we're sitting at 924. If I wind that out a bit more, 1 microsecond per division. Excellent. That's pretty good. Let's take her all the way to the maximum. Right, click up another one. It'll top out. That's a meg according. The raw output is a lovely square. It's a bit rounded on the amplifier one. Obviously, there's some distortion on that. Let's have a look, see what it looks like when it's a square. Well, it's a square. Let's try a sine. So let's increase. Yeah, there we go. We're triggered. Oh, that's beautiful. Look at that. That is beautiful. Let's make it a bit bigger. So we long press to get to the gain, and I'll click her up again. So it's maximum gain. Oh, I'm really impressed with this. Excellent. What about the other way? Wonder how we can get down to 0. See what it's like at the bottom end. If I reset the code, that'll get me back to a meg. I wind this in, and when I up that, there we go. So that is 1 kilohertz. Yeah, excellent. Let's wind her down. So let's go down in 100. So change this step and wind her down. Well, that's 300 hertz according to the LCD, and according to the scope 200, 100. Oh, spot on. Let's start winding it down in steps of 1 now. And we increase that. There we go. Well, there we are. That's thinks it's 19, and indeed that's what it says on the LCD. I'm really impressed with this module. Really impressed. Okay, that's this project done. There's code. There's the fritzing drawing. I will put it all up on GitHub, and I'll post a link down below. Hopefully you've liked this. Hopefully you think this AD9833 module from DollaTek, hopefully you're as impressed with it as I am. It cost me less than £10, and it's just the business. Also, really like these rotary encoders. When you get the libraries for them, they're really versatile. I mean, I've got single click, double click, long press, as well as the rotary knob itself. Absolutely fantastic. So, comments below. If you like it, tell me you like it. I love the likes. And in the meantime, until the next time, thank you very much. See you soon. Bye bye.